Hi.
Hi.
Hello. How are you?
Good.
Hi.
Hello, hello. Finals next week. Let's do this. Yeah, so yeah, it's scary. I have lab finals this week and lecture finals next week. And after that, winter break, rest, sleep, sleep, sleep. Sleep, eat, rest, rest. Yes, thank you. So today we'll do 8B first, and then we'll do 118A later in today's office hours. So Annie wanted to go over the e-mean formation part of chapter 17 study guide that you sent me.
Yeah.
Um, so
Or like the mechanism that we need to know. I don't know. It says they're very long.
right. The mechanism.
Mhm.
Before we go over that, let's first identify what an e-mean is with an I. Um, a carbonyl. Do you know what a carbonyl group is in organic chemistry? Carbonyl?
It's like the double bonded O.
Yeah, carbon, double bond, oxygen. An imine is going to be a carbon, double bond, nitrogen, right?
Uh-huh.
But this nitrogen here, to be neutral, it has to have three bonds. So this imine here could either be bonded to a hydrogen or it could be bonded to some random R group, some random hydrocarbon chain, right? So in this mechanism, if we go the forward reaction route, that's gonna make an imine from a carbonyl, right? If we go the reverse route, that's gonna convert an imine back into the carbonyl. So to convert a carbonyl into the imine, what we need is uh, either ammonia or a primary amine with trace amount of acid, right? Or dilute amount of acid. And I'll show you why we need dilute amount of acid when I go over the mechanism.
Okay.
That would convert the carbonyl into the imine. Now, if we want to convert the imine back into the carbonyl, what we need is some sort of acid and water, right? And the acid could be in the form of H3O plus, HCl, or H2SO4, right? So your carbonyl here, it could be a aldehyde or a ketone, or it could be a ketone, right? So let's say that we have this ketone here, and we are going to react it with this primary amine in trace acid, right? This carbonyl carbon here is electrophilic. There is a partial positive charge there, but this is a neutral amine that is a weak nucleophile, right? So this neutral amine that is a weak nucleophile cannot attack that electrophile by itself, right? Because this is a weak nucleophile, this is a weak electrophile. They cannot react with each other.
Mm-hmm.
So what we have to do to activate the electrophile, make this carbonyl carbon a bigger positive charge, is to protonate the carbonyl oxygen with the acid we have, right? And once we do that, that is going to give us this positively charged oxygen, which activated this carbonyl carbon. We gave that carbonyl carbon a bigger positive charge, right? And then
Mm-hmm.
because of that, this weak nucleophile amine is now able to attack that carbonyl carbon and pop the double bond onto that oxygen right there, giving us this tetrahedral intermediate, right? Now, once we form this tetrahedral intermediate, we're going to follow that common OChem mechanism pattern where we are going to do the deprotonate the group that we want to keep, which is the new group, and protonate the group we want to kick out, which is the new group, right? The new group that we just added here is this group right here, which is a good leaving group right now, but we want to keep it. So to convert this good living group into a bad living group, we have to deprotonate it. And the thing that I'm going to use to deprotonate it is just another amine right here. If you use like H2SO4, you could use HSO4 minus the conjugate base of that, but I'm just going to use another amine, another equivalent of the amine as a base to deprotonate that nitrogen right there to make it neutral.
What reaction is this similar to?
This reaction is imine formation.
It's
Right?
like it's kind of similar to like the reactions we did before,
Yeah,
right?
it's very similar to the carboxylic acid and its derivatives mechanism, like converting
Mm,
carboxylic acid to an ester or transesterification, converting an ester to a different kind of ester. Very
yeah.
similar to that mechanism,
Okay.
right?
Okay.
Um, so now once we deprotonated that, we have this bad leaving group, which is good because we want this group to stay. If we want this OH group to leave right here, we have to protonate it. And the thing that I'm going to protonate is just like another acid. You can use H plus or the protonated amine that we just protonated in the previous step, right? Whichever acid you could use to make that OH into an OH2 plus, good leaving group, right? OH2 plus. Now, once we have our good leaving group, to drive that good leaving group off, this lone pair of electrons on the nitrogen right there is going to go down to make a double bond between that carbon and nitrogen and kick out that group right there, right? And that's going to give us our iminium ion, a carbon double bond nitrogen that is positively charged because it has 4 bonds. Now, the final step here is just to neutralize it by deprotonating it. And we could use another equivalent of an amine base to grab that hydrogen. And then the bond between that hydrogen being grabbed and that nitrogen is going to break and go onto that nitrogen, which is going to give us this final product here, which is the neutral imine, the neutral carbon double bond nitrogen. And this ethyl group here attached to the nitrogen is this ethyl group here attached to that primary imine that we used in the beginning.
Mm,
Mm-hmm. If that was an ammonia, NH3, then this would be a hydrogen, right? If we used NH3 instead, but we used a primary amine where the R group is attached to the R group of the imine right there.
got it. Okay.
Mm-hmm. Now, let me give you some random imine, right? And then I want you to describe to me what would be the mechanism in reverse like reaction, right? Let's say we have H3O plus and water.
Well, I think that the whole NCH2 CH wait, whatever group is
Uh-huh.
gonna become a carboxylic acid group. So if that would predict the product, that would be the answer.
Yeah, so you're thinking of it as if this was a nitrile, like a CN, right? If that was a CN nitrile,
Mhm.
then that would be converted into a carboxylic acid, right? But what is this functional group here? A carbon double bond nitrogen.
Mm. So the whole like circle is gonna become oh what the
Right. What is this functional group here? When you have a carbon double bond nitrogen, what is the name?
carbonyl.
Not carbonyl, because a carbonyl is a carbon double bond oxygen.
Oh yeah,
Uh-huh. A,
nitr nitrile.
nitrile is going to be a carbon triple bond nitrogen. Carbon triple bond nitrogen.
What is it?
That's a nitrile. A carbon double bond nitrogen is going to be imine.
Oh wait, yeah, yeah, yeah. Wait, that's literally what I meant.
Uh-huh, imine, right. Um, and then if you do hydrolysis of imine, we're gonna hydrolyze this imine back into the carbonyl. So you know how this is the imine carbon right here, that blue carbon right there? When we
Mhm.
hydrolyze this imine with acid and water, that blue carbon is gonna be the carbonyl carbon of the carbonyl, like that.
Okay, okay. Yeah.
Right. Mhm. Okay, so now that's the final product. If we were to predict the products here, how now let's think about the mechanism. How would we get there in the mechanism?
I think the proton on N is gonna grab the H and
Oh
like
yeah, so the pair of electrons, not the proton, the
oh yeah,
lone
the electrons are gonna grab the H.
grab the H from the H2O plus, so it's gonna get protonated, right?
Mm-hmm.
Which makes that into a strong electrophile, like that, right? Okay.
Mm-hmm. And then I think the double bond is gonna donate its electrons to N. Or
Mm-hmm.
I
Yep, it will do that. But what will drive this double bond to donate its electrons to N? Like
if
once we
one of the hydrogens are taken away by the H2O on the side, so then it becomes a oh, wait a second, that doesn't make sense.
Yeah. One of the H2Os here are going to do something to this carbon, right?
It's gonna take a no. Oh, it's gonna protonate it.
Not protonate. It's going to attack it.
Oh yeah.
Attack.
Yeah.
Right. It's gonna give one of its pairs of electrons to make a bond between this carbon and oxygen right there. Right. Before that was
Uh-huh.
not able to happen because this is a weak electrophile. It's neutral. Right.
Oh, I see.
So the point of the first step here, when we protonated this imine to get this iminium ion with the positive charge nitrogen, is to make this iminium carbon a big positive charge, which allows this weak nucleophile, the one we have in the reagent, to attack that strong electrophile now, the
I
activated
see.
electrophile. Right.
I see.
But
And
that would
now
break.
it's gonna want to kick up the electrons to the
Yep.
end because it breaks the 4 bonds of carbon.
That's right. That's right. Mhm.
And then now that is a good leaving group, so it's gonna get. Let me think.
Right. So now once I have this tetrahedral intermediate, what would be the next set of steps here?
I think we want to kick off the end group, so we want to make it a good leaving group. So we're
Yep.
gonna protonate it.
Yeah, when we protonate it, we're gonna get NH2 plus, which is a good leaving group. We will want to do that eventually, but we won't do that first because when we do that first, we're gonna get two positive charges in the same molecule, right, which is
Mm-hmm.
unstable. We want to keep this group, but right now it's a good leaving group. So to make it into a bad leaving group, we have to.
The N is gonna wait. Let me think.
Mhm.
We have to attack it with H2O again.
Yeah. Attack the one of the protons, one of the hydrogens. Like we have to deprotonate it.
Uh-huh.
Right. One of the H2Os will not attack the positive charge oxygen. We want this positive charge oxygen to be neutral, right? A bad leaving group, because we want to keep this oxygen here,
Mm-hmm.
right? So to make this into a bad leaving group, we have to deprotonate it by using another water to grab one of its hydrogens, and then the bond between that hydrogen being grabbed and oxygen is gonna break and go onto that oxygen right there,
Mm-hmm.
giving us this intermediate here. OH, which is now neutral, right? Because it gained a pair of electrons, it lost the hydrogen, and it's neutral, bad leaving group, and that's good because we want that group to stay.
Mm-hmm.
Right?
Now we're gonna deprotonate it with H2O.
Protonate, H3O plus.
Yeah, protonate.
Right,
Oh.
protonate, right. Now we're gonna protonate the nitrogen with H2O plus to make this into a good leaving group. Right.
Mm-hmm.
Nitrogen. Now, once you have the good leaving group, what can drive that good leaving group off? What can drive this good leaving group off that we just formed right here?
Um, if we attack the carbon with another water to
Yeah. So once you have this good leaving group, look at the other atom attached to this carbon. What other atom has a pair of electrons at this carbon here?
oxygen.
Oxygen, right? And oxygen is going to use one of its pairs of electrons to make a double bond between that carbon and oxygen, because you know how our end goal here is to get this carbonyl, carbon double bond oxygen.
Yeah.
We're going to get that carbon double bond oxygen by this pair of electrons on oxygen right here going down to make a carbonyl, carbon double bond oxygen, between that carbon and oxygen right there.
Yeah.
Right. But that's going to break the octet rule for this carbon. One,
So
two,
then it's gonna
yeah.
push off the group.
Yeah. Push off the good leaving group that we just formed. Right.
Yeah.
Right. And that's going to give us this intermediate and this side product here. Right. Now the last step here is to make this oxygen that is positively charged right now neutral. How can we make this neutral? How can we neutralize it?
Deprotonate it with the water.
Yep. With the oxygen of the water. Right. Oxygen of the water is going to attack that and make it neutral like that. So that's the
Wow.
reverse mechanism.
Okay, so this was from imine to carbonyl.
Yeah, this was imine to carbonyl, the reverse way. The previous example that we went is carbonyl to imine, the forward way.
Okay, got it.
Yep. Same pattern. Like, first step is to make the electrophile strong, activate it to allow the weak nucleophile to attack to form the tetrahedral intermediate. And then once we have that tetrahedral intermediate, we do that whole proton transfer set of steps. We want to keep the new group, so we gotta deprotonate that. We want to kick out the old group, so we gotta protonate that. And then once we have that, the confusing step here is to like form a double bond from the other atom and then kick out the good leaving group that we want to be kicked out. Right? And then from there, we just do acid-base reaction to neutralize the final product.
Okay, and the predicted product is pretty easy for this because you just replace the N with the O.
Yeah, replace the N with the O. That's right. And then the R of the end, like he might want you to include this side product as well, which is organic, right? Which is the amine of like the R group here is this R group of the imine right here.
Got it.
Right.
Okay.
Yeah.
What about the imine cyanohydrin and hydrolysis one? What does he mean by in theory? Like we just need to know very specific small steps of it.
Imine cyanohydrin. Oh yeah. So this is what he means. So this is like one of the ways to make amino acid, which is Strecker synthesis. Right. Strecker synthesis, which is going to make an imine in the first step from a carbonyl and form a cyanohydrin looking like kind of thing.
What's a cyanohydrin?
A cyanohydrin is when we have an alcohol and a nitrile attached to the same carbon, like this. Right. So this carbon here is attached to a hydroxy group and a cyano group.
Okay.
Right. But I put it in quotation marks because this mechanism isn't really forming a cyanohydrin. It's forming a cyanoamine. Like, because instead of the OH, we're gonna have like a NH2. Right. So I'm gonna put that in quotation marks right there. And then we're gonna hydrolyze. We're gonna do hydrolysis to hydrolyze the nitrile into the carboxylic acid, like we said earlier. Nitrile is one of the cousins of the derivatives that when we do hydrolysis, we're going to convert that back into the parent functional group, the carboxylic acid. Right. So an example of structure synthesis to form an amino acid is something like this. Let's say we have this aldehyde right here, and I react it with 3 reagents, 3 steps. First step, ammonia and trace acid. Second step, HCN. You can see KCN as well, but I think HCN is just needed. And then third step, H3O plus, water, and heat. What would you expect as the first reaction due to this aldehyde here?
The oxygen is gonna grab H plus and become protonated.
Right. Okay. And what did that protonation step do to the carbonyl carbon?
It's gonna make the carbonyl carbon have a bigger like the positive charge.
Yeah, bigger electrophile, bigger positive charge. Right. We activated the electrophile.
And then the N is gonna. Oh wait, this is like kind of similar to what we just did.
Yeah, this is exactly what we just did right here, like the forward reaction of making the imine.
Okay, right. So then the electrons on nitrogen are gonna attack the carbon.
Yeah.
And push up the electrons on the oxygen. Okay, and then now we need to somehow make the. Let me see what I don't remember anymore.
So once we form this intermediate, the tetrahedral intermediate, this is when the proton transfer steps kick in, right? We want to keep the new group. So what do we have to do to keep this new group right here?
Deprotonate it.
Yes. And the thing that we're going to use to deprotonate it is another ammonia, another equivalent of ammonia.
Okay.
Because assume excess amount of ammonia here.
Okay.
Okay. Now that's neutral. How can we make this old group, the OH, into a good leaving group?
We have to protonate it.
Yep. And we could use ammonium ion, the one that we just formed, or trace acid in the environment.
Okay.
Okay. Now, once we have our ideal tetrahedron intermediate where the old group is a good living group and the new group is a bad living group, what should be the next step?
We have to kick it off. How do we kick it off? Oh, the electrons on nitrogen.
Yes. We have a good living group. To kick it off, electrons of nitrogen will go down to make a double bond between the carbon and nitrogen, kicking off that good living group that we just formed. That's right.
Okay.
Forming this iminium ion. And to neutralize it, we're going to use another ammonium ion, a third equivalent of it, to come in, grab that hydrogen, and neutralize that positive charged nitrogen. That's the end of the first step. We converted this carbonyl into this imine with the I.
Okay, got it.
Right. Now, when we bring in the second step, try predicting the mechanism errors here. It's okay if you don't know what will happen, but try guessing what would happen when we bring in HCN acid and KCN.
I think the electrons on nitrogen are gonna grab the negative CN.
So the CN minus is a negative charge, right? And this nitrogen with the pair of electrons is also negatively charged.
Oh, I
Neutral
meant like
bonds.
the hydrogen. Like it's gonna
Oh,
become
yes.
protonated.
Right. It's gonna get protonated from the HCN, kicking out that CN right there. That's right. You got it.
Nice.
Yes, and that will give us this iminium ion, which now, what can the CN minus do to this activated electrophile?
Attack it.
Yep. And that would break the octet rule, so we'll have to pop this double bond onto the nitrogen right there.
What's the difference between HCN and KCN? Why did you put both of those?
Oh, yeah, so you just needed HCN here, but some professors put KCN or NaCN. So I just put that there just in case you do see it, so you don't get thrown off. But you don't need the KCN. You could just react this with HCN to get the product that we want.
Got it. Okay.
Right. And that's gonna give us this right here, where I'm gonna put the NH2 up like this, and I'm gonna put the CN down like this, right? Where the hydrogen was, because I'm gonna make this hydrogen invisible now. I want to make it implied right here, somewhere on that carbon. Right. Now the third step here is gonna do a lot of things. It's gonna do a lot of mechanisms. But the third step, let's say, we have a nitrile here. And like you said earlier, what would happen to this nitrile when we react it with acid, water, and heat?
It's gonna. Oh. It's gonna turn into a a carbonyl.
A carbonyl, and what type of carbonyl? Ketone, aldehyde, carboxylic acid, ester, amide, isohalide, anhydride.
Amide.
Amide. So yes, it would become an amide in the intermediate, right? It would do that. But an amide is a derivative of what functional group? What is the parent functional group?
Carboxylic acid.
Yeah, carboxylic acid. So it's going to go all the way to a carboxylic acid, like that. Right. And because we're in acidic conditions, we're going to protonate the NH2 as well to NH3 plus, like that. Right.
Okay.
And then some professors, like, they draw out the amino acid where they deprotonate the carboxylic acid to give us this like deprotonated carboxylic acid and protonated amino group. And this is the R group right there of the amino acid. And that's the alpha carbon right there.
Okay.
So I would say helixes electrolytes because some professors, they add a fourth step of some kind of base like K2CO3 to deprotonate that carboxylic acid to get the carboxylate. But some professors do it differently. So I would check on how he does this Strecker synthesis here.
Okay, got it. Oh my gosh. And this third step is just like what we did for the second midterm, right?
Yeah, for the one with the carboxylic acid derivatives, hydrolysis. Right.
Okay. That was
Um,
my weak spot.
the weak spot. Let me give you one practice with that.
Oh yeah, okay.
Okay, let's
Sure.
do it. Let's see here. Let's do this.
For the imine cyanohydrin and hydrolysis, or is this just for the carboxylic acid?
Uh, carboxylic acid something like that unit, right? Let's say you have this reactant reacting with these reagents. How would you predict the product and the mechanism here?
Um, okay. Bro, I need to take out my note card for this actually. I can't.
Yeah.
I think okay, no.
I think you can do it without the note card.
Okay, fine, fine, fine.
I can guide you
The
through it. What is the
electrons
functional group
on
here?
electrons on the carbonyl are gonna be
Wait, to help you, what is this functional group?
carbonyl carboxylic acid. No, no, sorry. As
Ester, yes. And is that a derivative of a carboxylic acid, one of the family members?
yeah,
Yes, it is. So when we put acid, water, and heat, what would that convert into?
carboxylic acid.
Yes. So that is how you would predict the product, right? Recognize
Okay.
if it is one of the derivatives, and if it is, if it does hydrolysis, putting acid, water, and heat, convert that whole ester into the uh, parent functional group, carboxylic acid, right here, like that, right?
Okay.
So now you know how the difference here between this ester and this carboxylic acid is that leaving group attached to the carbonyl, right?
Uh-huh.
So we want to get rid of that OR group. We want to add in that OH group, which will come in the form of water,
Okay.
right? But right now, water cannot attack this carbonyl because it's a weak nucleophile and this is a weak electrophile. What can we do to make this electrophile activated? What can we do to make it stronger?
Protonate the
Yep.
oxygen.
Right. Nice, nice. To give us this protonated oxygen here. Now, once we have this activated electrophile, what should be the next step here?
Um now the now oh wait, give me a hint.
Yes, yes. Would you have a strong electrophile here? What nucleophile do you see on the weak
Aha!
side?
The oxygen on the H2O is gonna attack the
Mm-hmm.
carbonyl and push up the yeah.
Yes, you got it. You got it. Yay! Right.
Mhm.
And what kind of intermediate does that form? There's a specific name for this intermediate.
Oh.
Starts with a T. What does this look like?
Tetrahedral
Tetrahedral intermediate. Yes, yes. Because we have a tetrahedral carbon right there. Right. Now, once you have this, what do you think the next set of steps are gonna be? This is the new group. This is the old group.
we wanna make the old group a good leaving group.
Yes, we want to make the old group a good living group. We want to make the new group a
A
bad living group.
bad leaving group.
Which one would be best to start off with?
The old group.
Oh, so if we like this is the old group right here. If we protonate that old group to make it
Oh, I mean the new group.
yeah the new group because we want to get rid of
And
charges, right?
deprotonate it.
Yes. And what we could use to deprotonate is water.
Water, yeah.
Yeah. If you use H2SO4, then you could use H2SO4 minus.
Oh my gosh, you're so good. I actually understand this.
That's good. That's good. After this, I'm going to give you a very similar one, but I want you to run it through me step by step, all by yourself. uh-huh. Okay, what's next? What's next?
Now we have to protonate the
Uh-huh.
old group
Yes.
with
Uh-huh.
oh yeah.
With our acid that we have, H3O plus that we just formed back as well, right? And then once we have that, what would be next?
Kick off the leaving group.
Yes, and what would drive that leaving group to get kicked off? What other arrow can we
You
draw?
use either the water or the whatever to protonate one of the things so that
So we have our good living group here already, right? So we don't have to protonate or deprotonate anything anymore. We could use the pair of electrons on either alcohol, let's say this one, to go back down to make the carbonyl and kick out that leaving group right there.
oh, I see. Okay.
Because our goal here is to get the carboxylic acid. Right? OH, H plus. So that means our side product here is this alcohol that we just kicked out.
Oh,
Uh-huh.
okay,
Right.
got it.
Now, there's one more step here.
You can take the water and grab the hydrogen
Mm-hmm. And
and
not
then
bond to, yeah. Mm-hmm. Right.
okay.
Yes. Okay. Let me give you a similar one, but this time you run it through. Okay, so let's see here. Let's do this. Uh,
Oh my gosh, wait, when you change it into do you have to change the steric hindrance? I mean the not a, the what is the wedge dash thing called
oh,
again?
stereochemistry.
Yeah, the stereochemistry. Do you have to?
If nothing touches this carbon, it stays untouched. If something
Okay.
touches that carbon, and it depends on the reaction. If it's SN2, it inverts stereochemistry. If it's
Okay.
SN1, like you form a carbocation, then it would be randomized, racemized.
Okay.
Right?
Sounds good.
Uh-huh. Yeah. It might
Um,
just be there for decoration if it's not gonna be touched in the mechanism.
no, you gave me a different one. I can't follow the old mechanism, bro.
Well, it's the same mechanism, and it's just
Okay,
different.
yeah, okay. So you use the H2SO4 and the electrons will attack that HSO4.
Yeah.
Okay. And then it becomes a protonated OH. And then you're going to want to attack the activated thing, push it up. And then what's next? Let me see. Okay, so now you have H, you have O, H plus, and an OH plus. Oh, wait, no, you just have OH.
We have OH, OH2 plus, and the old amine group there.
Okay, so the water is going to attack the extra H on the plus one.
Uh-huh. And you could use water or you could use HSO4 minus to regenerate our acid catalyst. Right. It's best to use the conjugate base because when you use H2SO4, that's assumed to be the acid catalyst in the mechanism. But
Oh.
yeah, yeah.
Will Helix dock points off if I use it though?
I don't think so. I don't think Helix will do that. Yeah.
Yeah, he's so nice.
Yeah. Yeah. He's been getting mean for 8 series. 15,
Okay, wait,
16.
yeah, he's actually been pretty mean, not gonna lie.
This quarter.
Yeah. Um, okay, what's next? Then you use okay, now we want to make it a good leaving group, but what are we making a good leaving group? The NH part. So
Because what's our end goal here? Like it might help for you to think about what's the end goal. Like
we
what's
want to make it a carboxylic acid.
right.
Wait,
So
there's no
we know.
heat. Oh, wait, there is heat. Oops.
Yeah. I just added that in there.
Oh.
Yeah. Right. So if we want the carboxylic acid, what group do you think we want to kick out?
The NH.
We don't want that nitrogen there.
Yep.
Right. So what can we do to make that into a good leaving group?
Wait. Something with the acid. H2SO4
Right.
is gonna attack the electrons on N?
Other way around. Other way around.
Oh, the electrons on N is gonna attack H2SO4 and
Yes. Yes. Yes.
I see.
Yes.
Okay.
Yes. Don't make that common mistake, Annie.
All right. Oh, I that's a common mistake.
Yes. Yes. A lot of people make that mistake.
Dang, I don't want to be common mistake making.
And a lot of people also mix up wedges and dashes. Like I also used to mix it up all the time too.
Mm.
Wedges and dashes.
Okay, now the N is protonated
Yes.
because it has two H's.
Mm-hmm. Four bonds.
Okay, now one of the electrons on the O is gonna make a double bond and then
Yep.
kick out that leaving group.
Yep. Right.
This is so much fun. Okay, wait, and you're done. Oh, wait, no, there's a positive on the OH, right?
Right. Because this O right here that formed the double bond is still attached to the hydrogen, which is this hydrogen right here. Right.
Oh, so we want to
Mm-hmm.
take that
Mm-hmm.
off. So you use a water.
Oh yeah, water or HSO4 minus as a base to grab that hydrogen and
Oh,
make
yeah,
that oxygen neutral.
and we're done.
Yes.
Okay,
And
fun.
you, if this was predicted product, it's safe to put that leaving group as well.
Okay, got it. Okay. Wait, this is so much. Okay, so this was an ester to carboxylic acid.
Amide.
Oh,
Amide.
sorry, amide.
Amide, right.
Oopsie.
The last one was ester.
Yeah.
Right. Okay, that's good.
Okay, awesome.
Yeah. Mm-hmm. Okay.
Thank you. I don't want
Yeah.
to take up too much time.
Mm-hmm. Yeah, no problem, Annie.
Thank you, thank you, thank you.
Yeah. Yeah. See you, Annie. Hey, Elysia.
Hi,
How are you?
I'm doing pretty good.
Did Wei
Um,
finish her 118A content review, or are you guys like just reviewing final stuff now?
no, we're gonna review it on Friday. That's for the review.
Oh, that's
And
Friday. So you
then,
guys are gonna learn new material, like what, one more day or two more days?
yeah, we're just like cleaning up or like we're just doing the rest of like epoxides and stuff. So like
Hmm.
that's like the last stuff that we learned.
Yeah.
Um, I've been doing a lot of practice. I have my very last quiz tomorrow, but like I was watching the video or like
Uh-huh.
I guess the one that you just posted on H&MR.
Oh yeah, yeah.
And
I
it's
posted that one.
yeah,
Uh,
I that was the very question that my TA skipped because he said that's super hard.
oh,
And
compound A.
yeah, that one. He says he wouldn't expect to like
Yeah,
have
yeah.
that on
Because
the quiz. It's very
usually
complex.
the spectroscopy like has some kind of degree of unsaturation. It has some kind of double bond, triple bond, or ring. Right. That question that I went over that you watched had no degrees of unsaturation at all. It had no double bond, no triple bond, no ring. So it was pretty
Yeah.
difficult. Like, it took me a while to do it, but then I had to guess like the first time, and then I messed up because I when I was checking the H&MR peaks, I found out a mistake, and then like you just have to try different things and then hope it works. You gotta pray in the process.
Yeah, it's just trial and error.
Trial and error, yeah. Have you ever gotten one problem right, Elysia, like by yourself, like just trying it?
I almost did. I was just working on one and
Uh-huh.
I guess I got it wrong. Apparently, it was a long chain,
Uh-huh.
and it was like a carbonyl group, so it was like C7H14O. So I already know
Uh-huh.
there's gonna be a carbonyl group.
Mm-hmm. Yeah, that's good.
Yeah, but I was really close. I think I just need a little bit more practice
Yeah,
and
yeah,
like
to recognize
right
more
stuff.
patterns and make your own
Yeah,
like rules on like what you guess. Because like sometimes when you do these, you don't know where to start. But a lot of practice will help you just guess, like, take a shot in the dark and just go from there.
yeah, I know.
Yeah.
Yeah,
I know. H&MR is crazy.
yeah, it's
Mhm.
not a lot of people's favorites.
Yeah, no, no. It was my least favorite, and then my next least favorite was nomenclature. Like
Mm.
my favorite is a synthesis problems.
Really?
Yes, yes. Uh-huh. Is there anything that you wanted to go over in particular, Elysia?
Yeah, I guess either those notes or like if it's easier, I have examples that I uploaded into the
Hmm.
Google file. I
Hmm.
think it was more about epoxides.
Hmm.
I think
Yeah.
I think from last time that we we met, you briefly went over the concept or like the mechanism of epoxides, but we didn't really
Mhm.
get to cover a lot
Mhm.
of examples.
Yeah.
It'll be under resources, and it should be like epox or like labeled something under class resources. Yeah, that one, the epoxides
Oh,
PDF, I think.
epoxides PD. Oh, here, I see it. Yeah, yeah, yeah.
I think so.
Yeah, yeah. Yeah. Uh, let's go over the practice problems. So then I can teach you the content through them. Because I feel like that's smoother than just me teaching you like straight from the scratch, like from the beginning.
Yeah, yeah.
Uh, hmm. Okay, that's the key. This is the practice right here. This is the mechanism. These are the notes, I guess. Yeah, notes. These are the practice problems here.
Yeah, I found this like I thought it would be like helpful for like practice. I just got it off of I think it was Edna's
Mm,
resources.
mm-hmm.
Either
Yeah,
Edna's or Mariah's.
yeah. It's good. Right. Okay, so let's do this one by one, and I'll give you similar ones after we go through these. So when you have an alkene on the molecule like this, and you see RCO3H, which looks like this, right? This is a peroxide bond, which is super unstable. And because it's super unstable, it's super reactive, right? And then a type of RCO3H is going to be MCPBA, right? But you're going to learn more about this in 118B when you learn about alkenes at the beginning of the quarter, right? But what this would do is that this would turn an alkene into an epoxide, right? So if you were to focus on the alkene carbons, which is this carbon and that carbon, and you look at the product here, those two blue carbons right there are the epoxide carbons, right? And when we add the epoxide in there, they have to be cis to each other. Like they both have to be either wedge or a dash, right? And in this case, since we both decided to make these bonds wedge, the hydrogens here are forced to become gaseous, like that, right? Now, we could open up epoxides in either acidic conditions or basic conditions. And do you know or do you remember what the differences are when we open it up in different conditions? It's okay if you don't remember.
Yeah, there was one where I think it's acidic is the one where it prefers the the most
Uh-huh.
substituted, and then the other one is least substituted. Where in basic conditions,
Yes, that's
I
correct.
think.
Acidic conditions prefers to attack the more substituted side of the epoxide, and the basic conditions prefers to attack the less substituted side of the epoxide. That's correct. In this case here, it doesn't really matter because both carbons of the epoxide right here are equally substituted, right? Because they are both attached to one other carbon, right? So the nucleophile here is going to attack either carbon. Doesn't matter. You get to choose, right? But let's think about the mechanism here. We are in acidic conditions because we see that strong acid there, H plus. When you see a strong acid, we're going to look for the strongest base to react that strong acid with. The strongest base in this molecule is going to be this oxygen with two pairs of electrons. This oxygen with two pairs of electrons is going to attack this hydrogen with one of its pairs of electrons. So it's going to grab that hydrogen with one of its pairs of electrons. It's going to make a new bond to that hydrogen using that pair of electrons right there, right? And in the intermediate, this is what we'll get right here. We'll get that decoration ring, this epoxide bond with the oxygen. I'm going to leave these hydrogens as invisible, but we know that those hydrogens are dashes, right? This oxygen here grabbed a hydrogen, which this new bond here that we made between that oxygen and hydrogen, those two electrons came from this pair of electrons right here, right? And so that means that this oxygen here only has one pair of electrons left. And what would be the formal charge of this oxygen with 3 bonds and one pair of electrons here?
Is it a positive?
Yep, positive charge, that's right. So once we have made this positive charge oxygen, these carbons here of the epoxide are now more unstable, right? Because charges would make molecules less stable. And because this molecule is less stable, the carbons of the epoxide here are more reactive, right? And if this was a more substituted or less substituted situation, then the positive charge, let's say there was a methyl group here, would reside at the more substituted position compared to the less substituted position, right? Because if you think of this as an SN1-like mechanism, if you kick off the good leaving group there, the carbocation is going to be most stable at the most substituted position compared to the carbocation at the less substituted position. So in acidic conditions here, I'm going to draw out the ethanol out like that. This oxygen here of the ethanol is going to be the nucleophile because it has pairs of electrons that it could use to attack that carbon, right? And that's going to break the octet rule of that carbon because this carbon has 1, 2, 3, 4, and then this oxygen here is trying to make the 5th bond right there. That's not good. So what we have to do is we have to break open that epoxide and give the 2 electrons of this bond onto that oxygen right there, right? And think of this as an SN2 backside attack. What would happen to the stereochemistry here if we're doing an SN2 backside attack here?
Inverse stereo.
Yep, inverse sterochem. So this wedge would be inverted to a dash. This is the oxygen of the ethanol right here. That oxygen is attached to an ethyl group, which is this ethyl group right here, and a hydrogen, and it has one pair of electrons, making that oxygen positively charged. This OH right here maintains its wedged bond because nothing touched that carbon, right? And this oxygen here is now neutral because it gained a pair of electrons from that bond that got broken off onto that oxygen right there, right? Now, the last step here is to just use another alcohol to deprotonate this positively charged oxygen to give us our neutral product here. Does that make sense?
Yeah. And then we said that the OH came from when the lone pair bonded with the H plus.
Oh, this OH right here?
The other one, the one that attacked.
Oh, this ROH, ROH.
Oh, ROH.
Alcohol?
And is
Yeah,
is that the one that came after this? It's the second step? Okay.
yeah, that's the second step. The first step is to protonate the epoxide oxygen. The second
Mm,
step is to bring in that alcohol to attack one of the carbons here. And if it was more versus less substituted, it would attack the more substituted carbon.
okay. And then can you repeat the last step real quick, please?
Yep, So once we get here, um, with the positively charged oxygen, wait, do you get why this is positively charged right here, this oxygen right here?
Yes.
Yeah, to make it neutral, we have to deprotonate it, right? We have to get rid of this hydrogen and give this oxygen a pair of electrons. And that pair of electrons is going to come from that bond right there. So this alcohol here is the second equivalent, second mole of it, right? Because we have an excess amount of alcohol. We're going to bring in a second equivalent of it as a base to grab that hydrogen. And then as this oxygen here is grabbing that hydrogen, the bond between that hydrogen and the bond between that hydrogen and oxygen is going to break and go onto that oxygen right there, right? The 2 electrons from this bond right here are going to go onto that oxygen, making that oxygen neutral, right? And then if you were to draw out the conjugate acid of that, it would look like this. But we don't worry about that. We worry about this more, the major product,
Okay,
right?
that makes sense.
Yeah. So the last step here was an acid-base reaction. This is the base, this is the acid, to deprotonate or neutralize this positive charged oxygen to make it neutral. Right? It got rid of a hydrogen and it became neutral.
Right,
Right.
and it's because we brought in a second equivalent as a base to deprotonate and stabilize the oxygen.
Yep, that's right. Right.
Okay, that makes sense.
Uh-huh. Yep. Okay. So let's check the key here. Where is it? Right here. Yeah. Let's see mixture. Okay. So this is one of the answers that they gave us, right? But you know how I said it didn't really matter if you attack this top carbon or bottom carbon?
Yeah.
If you attacked the other carbon, you would get this product here, where the OR group is going to be at the bottom side, and the OH group with the wedge is going to be at the top side, right? So this right here would be a different type of molecule, right? Because they have a different stereochemistry, right? Because if you tried like flipping this molecule over upside down, that would not be equal to that molecule there. Those are different molecules, right? Because if you assign R and S for this car center versus this car center, they would be different, right? This product here that we got originally was when this alcohol, the first equivalent of the alcohol, attacked that carbon right there at the top. This second product here that I just drew out is if this alcohol attacks the bottom carbon instead, inverting the stereochemistry at the bottom carbon into a dash OR, and then the OH at the top right here is going to become this OH right here. Right, so I didn't draw out the mechanism for this product, but this is the other product you get if the alcohol attacked that bottom carbon right there.
And would we have to include both?
It's safer to do so. It's safer to include both. Yes. Yes.
If we did, would we have to label like a major or minor?
In this case, no, because they're both going to be equally major.
Okay.
Right? Because there's no more or less subside. If there was a more subside, then you don't have to put both. You only have to attack the more subside, and then you don't have to worry about anything else. But in this case, you know how both carbons here are equally substituted? That would
Yeah.
make things different, right? You'll get two different products here.
Okay, that makes sense.
Uh-huh. This is electrophilic addition. Electrophilic addition. Oh, this is epoxide opening. Epoxide opening. Electrophilic addition is for alkenes. So you can think of this first reaction here as electrophilic addition to get the epoxide. And then once we have the epoxide, we're going to open up the epoxide in acidic additions here. Right. Uh-huh. Okay. Oh, now let's think about this one right here. How would you think about the mechanism for this reaction here? In this case, we do have a more and less subside.
Um, I guess we have to see if our nucleophile is a good or weak nucleophile.
Yep, yep. You can think of that, or you can also think what kind of conditions we're in, acidic or basic, based on these reagents here.
Acidic, I think.
Acidic conditions, right? Because we have a strong acid, sulfuric acid, H2SO4 here. So, what would that strong acid do to this epoxide here?
It will go to the more substituted side, which I'm assuming would be the top one with the CH3.
Yeah. So, if you were to predict the product, it would go to the more substituted side. So when this methanol here attacks the more substituted side, we're gonna break that bond right there. And you notice how this bond right here is wedged right now? When
Yes.
we invert that wedge into a dash, we're gonna get this dashed O, which is this O right here. And what is attached to this O right here?
The OH, or are we talking about lone pairs?
We'll talk about the group. So OH is part of it, but that's gonna get deprotonated in the mechanism eventually, right? That H is not gonna be there anymore. Because I'm gonna show you where that H goes in the mechanism. But what other thing is attached to the O besides the H? What other group?
The CH3, the methyl.
Yep, the CH3. So we could put that CH3 right there. Right. That's gonna force this CH3 of this carbon that was a dash before into a wedge like that. Right? Because we inverted the stereochemistry into a dash when we added that OR group to that more subposition. This carbon here was untouched, so that would maintain its wedge bond, and that's going to become OH right here, where that OH is going to come from this oxygen right here. Right. So if you wanted to predict the product quickly, this is what you would do. But to do the mechanism, we have a strong acid here. So that strong acid would protonate the epoxide oxygen. It would protonate this epoxide oxygen here, giving that oxygen a positive charge. Right, because it gained a bond to hydrogen. So because it has 3 bonds and a pair of electrons, it's positively charged now. And now if you think about this in SN1-like mechanism, there is a bigger positive charge at the more sub position, a smaller positive charge at the less sub position. So when we bring in the nucleophile methanol, CH3OH, that we have in the reactant in, that methanol is going to attack the more subcarbon, this more subcarbon right here, right? Because there is a bigger positive charge there. But when we do that, we're going to do a backside attack and invert the stereochemistry when we break open that epoxide and kick that off like that, which is going to give us this intermediate here, right? So when we invert stereochemistry, that wedge turns into a dash. That oxygen right here is attached to a hydrogen, like you said, a CH3, and because it has 3 bonds, it's positively charged. This dash methyl that was there before is now going to become a wedge methyl like that because we inverted stereochemistry at that carbon. This carbon got touched, so it's going to be inverted. The carbon, on the other hand, is going to maintain its wedge bond to an OH, right? This OH right here is this OH right here. This oxygen right here was positively charged before, but it is now neutral because it gained a pair of electrons from this bond that was being broken off, right? Where the last step here is to use the conjugate base, HSO4 minus, to deprotonate and neutralize that positively charged oxygen to give us our final answer, where the OR group is at the more subside because we are in acidic conditions here.
I'm kind of confused on the like last step or like the transition from the second to the last step.
Oh, from this to this right here?
Yeah.
Right. So once we get this epoxide that got protonated with a positive charge, right? These carbons of the epoxide right here are more reactive now because this oxygen is positively charged. So that makes this molecule overall less stable, more reactive. So now this weak nucleophile right here, the alcohol ROH, is going to come around, which is that weak nucleophile right there, and it's going to decide to either attack the more subcarbon or the less subcarbon. And it decides to attack the more subcarbon because this more subcarbon here has a bigger positive charge. Positive charges prefer to be in more substituted spaces, right? Because it's more stable at more substituted spaces. This is the more substituted carbon because this carbon here is attached to 2 carbons. 1, 2. This carbon here is less substituted because it's only attached to 1 other carbon. 1. Right. That's why there's a smaller positive charge at this carbon because it is less substituted. Right. Whereas this carbon here at the top has a bigger positive charge because that carbon is able to stabilize that positive charge more since it has more substitution, more substituents, more R groups. Right. Does that make sense so far on the differences between the positive charge size between this carbon and that carbon?
Yeah,
Right.
that makes
So now,
sense.
once we know that difference in positive charge size, we know that this top carbon here is the better electrophile, right? Because electrophile is positive charge, right? So this nucleophile here is attracted to this better electrophile. So that's why we're going to attack that more substituted position in acidic conditions, right? But it's going to do it in a backside attack. So when we attack that carbon right there, we're going to break the octet rule, right? Because we're trying to make a new bond between this carbon and that oxygen right there. Right. So when we make that new bond right there, let's say, for example, we're gonna have 5 bonds. 1, 2, 3, 4, 5 bonds. That's not good. That breaks the octet rule. So to conserve the octet rule, think of this as the good leaving group. We're gonna kick off that leaving group like that when we do it, like when we attack that carbon right there. Think of it as an SN2 like mechanism. Does that make sense? Like when we attack this substrate, we kick off that good leaving group right there, right? And because it's SN2 like mechanism, we're doing a backside attack, which is gonna invert that wedge into a dash. right? We're going to invert the bond that we're breaking off here, which is this wedge, into a dash. Right? Does that make sense?
Yes, it
Right.
does.
Yeah. So the next step here, this is the new bond that we formed right here. The new bond that is a dash between that carbon, and this is the oxygen here of the alcohol right there. And we see that that oxygen is attached to a methyl group, which is this methyl group, and a hydrogen, which is this hydrogen right here. Does that part make sense?
Uh,
Yeah, right. Now, because this oxygen has 3 bonds, it is positively charged. And also, this methyl right here that was dashed before also gets inverted to a wedge, right? Because we are reacting at this carbon right here, so that carbon, everything would be inverted at that carbon. So that's how we got from this structure to this structure here. And also, you could think about the positive charge oxygen here. That positive charge oxygen is this neutral oxygen right here right now. It became neutral because it gained a pair of electrons from that bond right there. And then this wedge bond right here was always there before, which is that wedge bond right there. Like that. And then this hydrogen that's dashed, I just left that as invisible. It's right here somewhere.
okay, I think I get the inversion of stereochemistry. I just don't get like the nucleophiles that are hitting it, like the OSO3H. I
Yeah,
don't
right,
understand
right.
that part.
So what atom is attacking this carbon here? What atom is attacking that more subcarbon?
It would be the oxygen.
The oxygen right there, right? So if I store this oxygen here like that, making that nucleophile, and dot this carbon right here, making that electrophile, we're gonna make a new bond between the star and dot. The new bond between the nucleophile and electrophile. So this is the starred atom. This is the dot atom. That would make this the new bond right here. Does that make sense so far?
Yes, it does.
Yes. Right. So now, if we look at the starred oxygen right here, this OCH3 right here, that CH3 right here is this CH3 right here, right? And then this O is also attached to a hydrogen, an H, which is that H right there. I just drew it out in this way. Like before, we did not see that bond between the O and H right there, right? But I just drew out that bond between O and H just so that I could show the mechanism more clearly. Right. So this whole thing right here is this whole thing right here. Like if I highlighted this CH3OH, that's going to be this CH3OH right there. Right. But this oxygen here is now positive charge because it gained a bond.
Oh, okay, that makes sense.
Yep. Right. That's good.
And so is like, are we imagining the OSO3H, like the negative one that's floating? Is that like
Oh, this is not
um
negative. This is neutral. This is neutral.
or like the other one on the last step? Like
Oh,
when
this is
I'm
oh okay.
assuming, yeah, that part.
This is the conjugate base of H2SO4 because you know the very first step
Oh,
here is to protonate the epoxide with the H2SO4
yeah.
that gets kicked off as HSO4 minus.
Okay, yeah. I was a bit confused on like how that was 'cause I could assume that H2SO4 and that one were somewhat similar. I didn't know how to
Yeah,
interpret that.
right. I just drew it this way because like that's how I learned it from the tutor that was in the Discord that taught me when I took the class.
Mm,
He drew it like this all the time because that like represents the negative charge on the right atom more like clearly, but that represents this HSO4 minus right here from this H2SO4
oh,
because this is
okay.
right here. Yeah,
Yeah.
right.
Okay, that makes much more sense now. I think
Yeah.
that's where I was confused.
Uh-huh. And then
Thank
that's
you.
gonna regenerate our acid catalyst H2SO4.
Okay,
Uh-huh. Yeah, no problem.
thank you.
Yeah. Okay. So um that's good. Were you able to learn this, Wiley? Did you already finish this epoxide stuff, Wiley? Or what are you on right now for your class? Uh, E1, E2. Oh yeah, Cody. The order is weird. So you're starting to learn like SN2, SN1, E1, E2 reactions. Let's see. But she only covered E2. Yeah, E2 is the harder one in my opinion because there's anti-periplanar transition state. There's Hoffman. There's Zaitsev with the different kind of bases. Yeah. Right. Let's see. I haven't learned Python or that stuff. Dang. What topics would you guys want me to focus on the 118A final review session? Like SN2, SN1, E1, E2, epoxides for sure, HNMR maybe.
I feel like I don't really see H&MR covered in like class. I only ever see it in the discussions like
Uh-huh.
quiz.
Discussion quizzes, yeah. But it will definitely show up on the final.
Oh my gosh. Okay, that's good
Yes.
to know.
Yeah. So
Yeah,
so practice.
probably. Do you think that's like it'd be like the interpretation, like how to draw the structure out?
Yes, yes,
Or
that's most likely it. Like
ah,
they'll give you the IR, the HNMR, the chemical formula, and then you have to draw
oh
out that structure
no.
based on all those information.
Okay, then that's kind of good that I got my quiz tomorrow because I'm like
Yeah.
working on that.
Uh-huh.
Yeah, I think like maybe going over however many mechanisms, like
Mhm.
that's possible. I mean, like I guess like they're the main ones are similar, like I guess like the SN1, SN2, E1, E2. Those ones are
Yeah.
like they apply to the majority of the other mechanisms, but maybe like if there's some ways that we can like make those connections or like
Mm-hmm.
apply those to the other
Reactions like
mechanisms.
ether
Yeah.
reactions, epoxide reactions. Uh, yeah.
Yeah, I
And
think
Wiley is over.
that would
Huh?
help a
Yeah,
lot.
yeah, yeah, yeah.
Oh no, I was just saying that would help a lot. Yeah.
Yeah, yeah, yeah. I'll definitely go over that. And I know Wiley is when 128, and he already learned some 118B stuff like alkene reactions, like electrophilic additions. So
Mm,
uh, I don't know if I'll go over that. I'll probably focus on more 118A stuff, Wiley, because like most people there will be 118A people. Yeah. Uh-huh. Yeah. So then I can help you with the newer material, like SN2, SN1, E1, E2 stuff. Yeah. Yeah, yeah. That's good. That's good. Okay. 118A material, Goofy. Yeah. Like the spectroscopy. Spectroscopy is like the one that requires the most amount of practice to get used to. I hated it so much. Less straightforward, yeah. Okay. Good luck, Alicia, on your quiz tomorrow. And good luck, Riley, if you have anything this week. And good night. Good night. Oh yeah, you have a quick question, Sulisma? Yeah, yeah. What?
uh, yeah. I know you're probably really busy and all. I was trying to look to see if there was like any time that you had available for like a single session. I saw on your calendar it's like completely booked, so like I understand
Mhm.
if it was like that, but
Yeah.
just wanted to put it out there if it was possible. But if not, it's totally fine. Like
Right.
you'll see me on the on
On
the
Saturday.
weekend.
Right,
Yeah.
right. I could do Sunday, anytime like 2 p.m. to 5:30 p.m.
Okay.
2 p.m. to 5:30 p.m. if that works with you. Sunday.
Yeah. Okay. I will most likely be free like all Sunday, so
Oh,
I'll
Sunday.
let you know like a more specific time.
Uh-huh. Right.
But yeah. And then uh okay, and I think like the payment is like still it's linked to your all of your to your site, right?
Yeah, so the payment for the scheduling sessions Calendly will be for that, and since Calendly is like fully booked, I put it like that because I like put nothing in on Sunday.
Yeah.
So then if you wanted to schedule with me, just let me know on Discord, and then I could just send you my like Venmo or Zelle, or whichever one works best.
Okay, okay, yeah.
Yeah.
I know I was thinking about scheduling. I was just like
Uh-huh.
time time goes by so quick. Like
I
it's just a
know.
lot. Yeah.
Uh, yes.
So I'm sorry if like I'm taking up your time.
No, no, no. It's okay. It's okay. And also when you do schedule the session and you let me know what
Uh-huh.
topics you want to go over as well, and send me the resources so that I can like prepare some notes and practice ones for you and
Yeah.
homework for you after the session for you to try get as well.
Okay.
Uh-huh.
Okay, thank you so much,
Uh-huh.
Brian.
Yeah, no problem, Alicia.
Thank you. Have a good night.
Yeah, you too. Good night. Good luck
See
tomorrow.
ya. Thank
Bye.
you. Bye.